Cool. Well, welcome everybody to what month is it? It's been that kind of time. And I'm not lying, I
May.
was late because I am at a hospital. So that's, how much I love the Distributed Systems reading group. Um, but yeah, it's in May. That's true. Um, and yeah, sorry about last month. A bunch of us were in various conferences doing a bunch of talks at IPFS thing and Computer Over Data Summit and some other stuff. I think in the middle in there, April was pretty packed with a bunch of stuff. So really didn't get a chance to get time to get a paper through, but we're on track now for the next few months. And actually, with this paper, and we'll see, I want to get some people's thoughts on this. This is a thread that's very important to us. So this paper actually came, actually I talked to Chris Micklejohn about this paper, the Ambrosia paper, which again, I linked in the chat, his really good post on this. There's a lot of, he's on this paper. So, that's one thing, but it's one that he brought up to me when we've been looking at stuff that we've been doing at Fission for this project called Homestar, which is implementation of a thing called IPVM, which is essentially, it's a lot of things, but at its heart, I guess it would be a kind of a workflow engine that works over like IPFS and decentralized data to do compute jobs and compute functions. Think of it like Lambda, decentralized Lambda. But when I say the word Lambda, and I'm guessing people here, you can tell me have had some experience with Lambda or something like serverless functions running on a stack like this, or maybe it's Lambda under the hood, or Azure functions, I guess that's what they call those. There's not a lot of guarantees that these systems actually make about how compute is coordinated or how it works and how it fails. Things just kind of fail and you have to restart them or rerun them. This paper, Ambrosia, though not specifically serverless, comes through a lot of work that Microsoft has been doing over the years around things like durable functions, durable tasks, durable entities. Ambrosia is a little bit of a different project that's peer-to-peer. But it deals a lot with this concept that is in through all this work at Microsoft, really, which is, virtual resiliency. Actually, I'll start this by actually let me share my screen of a talk I was working on that I gave in Boston pretty recently. We're really into this. Brooke, who has also shared this paper across many talks, and I just share this keynote here. So I bring this up a ton. So we've been, this is the line that I wanted to bring up, and something that Ambrosia, I think, is a lot about, which is, at Fission, we're really interested in when things go wrong and what that means for users. And I think Ambrosia really is toward this idea. I share this slide here, talking about things like self-RPC. How do you deal with non-deterministic code, right? With determinism, you get a lot of replayability, but you want to be able to actually reason about non-deterministic things in a replayable, almost deterministic way. And that's really the core crux of this paper. I just kind of wanted to share that as we're sharing stuff. So I'll open it up now, or maybe does anybody want to give, who has read it? Maybe I will pick on Brian if no one else says anything. A little bit like 10-minute presser about this paper, and then we can open it up to see what people kind of thought about it and stuff like that. But I'm guessing it'll be Brian. But and anyone else you have like a minute, like a second to let us know.
Okay, I'll give it an attempt.
Yeah.
So, I think you kind of, in your intro, I think you actually did capture sort of a summary of a lot of it. Really, it's about building a system for distributed a system for distributed systems where you can be what they call failure oblivious, and Micklejohn has this up at the top. And really, a lot of this is the idea is based on having a durable log where you're logging the progress of the system. And if failure occurs, somebody can jump in and take a look at that log and kind of read through it and get, up to speed with what happened maybe before they failed, but what happened in the time that they failed. And there's this really sort of clever system of primaries and secondaries, where a primary is, some actor in the system that's live and is like, working on things. And if they ever lose the lock, then they lose their status as a primary and somebody else jumps in. And that leads to, there are some other cool things that kind of fall out of that. I mean, the logging in general, like time travel debugging is really cool. One thing that I thought was really great was the way that blue-green deployments kind of happen just automatically, what do they call them? Service updates, where it's like,
the rollouts and stuff are,
yeah. And it's just because, I mean, that's, like, that's kind of what's happening with the primaries and secondaries and whatever. And so if you want to like have a new deployment, then you have somebody come in as a secondary, and eventually it's their turn and the system just naturally sort of upgrades. That seemed like a good summary.
That covers good. Yeah, that's good. No, for sure. Yeah, there's a lot of interesting stuff with, and I don't see how we go into details around immortals. I mean, a lot of in the Ambrosia system is something that we think about a lot. There's like actually dealing with kind of storage and compute, but there's also these ideas of having coordinators, and coordinators are the ones kind of dealing with, to your point, with all this kind of primary, secondary handling. The one thing I'll call out, which well, I want to like define this. I think this is really important to this paper. So like the one takeaway anybody could get, because we're using this term a lot, is this idea of virtual resiliency. And this is where like it was coined, right? And so I'm just reading off my notes here. You can see I'm not lying. I have these notes on my iPad. So I give the formal definition initially in the paper. I think it's here as I'm sharing it, but in this paper, we coined the term virtual resiliency, which provides developers the illusion that machines fail by automatically fully healing the system after physical failure, analogous to how virtual memory provides developers the illusion that physical memory never runs out automatically by automatically paging memory to disk. So while most data processing environments perform efficient programming execution environments, but perform some kind of virtual resiliency, there's no common analogous system for this kind of general purpose distributed programming. I think, this one thing I kind of want people to get out of this paper is that there's a lot of great systems papers. There are not a lot of great systems papers that really capture a quality, or I think virtual resiliency is this kind of quality that you want to capture more generally. And I know people have worked in workflow systems like Temporal or Uber's Cadence or things like this, where they try to capture them. This is, again, this whole like kind of Microsoft influence over the industry for this stuff. But this idea of virtual resiliency is, it's something we've been really harping on, which is like working with distributed systems for the developer, from the developer's perspective, should feel, they should not be tasked with having to handle every possible failure, everything. It should almost feel like the way we work with memory today, right? To that whole point. And so I want to maybe open it up right now before we get into the kind of intrinsics around deterministic replay and these really kind of working with non-determinism, which is in language heterogeneity, which this paper is really about. I want to open it up to people, what does that mean to you when you hear this kind of virtual resiliency? I want to say it's not a pie in the sky thing. It's a real paper with real systems, but I leave it open up to someone to kind of go off that. Anybody? Paul Burrell, he's around. But yeah.
Sorry, I was my mute was on. Well, okay, so I am vaguely familiar with this paper, but I must admit my memory is not doing so great right now to remember the details. But what I do know is that this whole idea of virtual resiliency, the great term, by the way, is something that we've been digging deeply into for 20 years at 3 or 4 different companies. And it's kind of what hardware and software engineers have tried to do for a very long time. And we failed miserably. We failed with disk drives. We never got them to perform properly. I used to work for a disk drive company. It's embarrassing how bad the implementations are. We've failed with SSDs. We've failed with F-Sync. It has all of these awful failure modes that that stop systems being idempotent when they're supposed to be. And so it really comes down to one thing in my mind, and that is, can you do things atomically or not? And so, that's the kind of angle we've been coming at from this virtual resiliency for the last decade or two. And I think it's an incredibly great research area. But I also think that the solutions already exist. I think if you go and talk to the best people in all the different companies, I'm not talking about, things databases that don't really perform or are not really resilient like Oracle. I'm talking about people who really try hard to guarantee the resilience of their systems. You'll find that they focus on atomicity, and it's atomicity in a distributed system. Do I get exactly one semantics, across a distributed system?
Yeah. The panacea of exactly one semantics, right? Yeah, exactly. Yeah.
Anyway, that's my initial response.
Yeah, that's great. No, that's great. And I think, one thing I did highlight in this paper, and I talk about, I think the key in this one is obviously, how I, in talking to Chris Micklejohn and how I came to read this paper was, we were looking at all these workflow engines. Again, I mentioned Temporal, Uber's Cadence. You can go back to like Apache Airflow. And actually, this paper does a good job of actually talking about a lot of distributed system compute, focus on compute and processing. Historically, really can take a lot from what we've learned about storage. We talk about a lot of this in this paper. And it's like, I think in distributed systems for years, people kind of forgot like all the wins that storage kind of gave us to think about those things. And then we didn't always apply them. They eventually did, of course. And I think, these are culmination papers on this. But I think the biggest thing too is like talking about working with many languages is something that we think a lot about at Fission, right? Like people should be able to like work in a language that's familiar with them. So this kind of language heterogeneity thing I think is really interesting. But yeah, I think to your point, Paul, too, it's like, it has it, I think we have all the components, we have all the pieces, but there hasn't been, I think only in since some of this work and, virtual resiliency, again, this great term is that we're finally putting words to how to quantify what this means. Right. So I think that's why I think this paper is really amazing. Minus some of, obviously a really great evaluation. There's a quote that I have to call out, which is one of the coolest quotes. I'm going to definitely steal this, maybe without citing them. We'll see on video. But there's a quote when they get to the evaluation, which I think was my favorites, which is, of course, theory and practice are not always the same in practice, which might be one of the best sentences I've ever I've ever come across. So I thought
today
this paper is really, yeah.
Today happens to be the 50th anniversary of Ethernet, and in fact, later this afternoon.
Actually, today,
yes. And I'm on my way to the Computer History Museum this afternoon, and I've been invited to be part of the ceremonies there this evening, which I'm really looking forward to.
Yeah, you were mentioning. Oh, so today's the day. Wow, amazing.
But it reminds me of a saying that Bob Metcalf came up with. He said that Ethernet doesn't work in theory; it only works in practice.
That's right. Yeah, exactly. That's great. Yeah. And so I was saying with like, for these things, again, where this paper came for us is we were looking at, Chris himself does a lot of research and work at DoorDash these days. And they're one of the biggest purveyors or users of Uber's Cadence, again, one of these workflow systems. Maybe, Brian, if you can put some of these links in the chat, that would be good, so I'm not talking in air. I can put them in later, too. I'll do it shortly, if anything. Uber's Cadence, and then Temporal, yeah. And so, in these systems, they obviously are really into the, really trying to take advantage of exactly one semantics for compute in workflows. They basically have a lot of language in their documentation about, what does it mean to be idempotent? What does it mean to have determinism, and how does replayability work? But then when it comes time to working with these things called activities, and this comes from another line of Microsoft research stuff, again, durable functions, durable tasks, durable entities, they didn't want to like have to force the user or think about some of these things. They do some things like random time of day, these things become wrapped. They recommend you to use, temporal's version of get time of day or temporal's version of get random. That's specially wrapped so that they can do replayability for obviously those things we know as being non-deterministic. But when you write these workers in this code, it's a very this is very much microservice kind of architected compute frameworks, these temporal and cadence, what they are, is that it doesn't stop the programmer from doing bad things like using the system's random, which then throws replayability out the window, right? And so, I think this paper and a little bit, they're able to do a lot of this because they're within a controlled environment within Microsoft and Azure, where they can like also force a lot of tooling around C#. And they talk about this in the paper. There's a lot they can bake into the bindings, which can prevent users from doing the wrong thing to some degree. And so that's like another major part of this. And again, why we came past it was in looking at something like building a decentralized compute engine. How do we work with replayability when people can kind of do anything they want? We can just tell them you should be deterministic in your code, but cool. How many times have you told a developer like they should do that? And I've now given a couple talks on this. There's still a lot of developers who don't know the difference between determinism versus idempotence versus impure, and these kind of things that come up. There's a really, and I'm okay saying this on camera, I think, a somewhat insightful but kind of horribly done video by the people at Temporal where they talk about like a video like what is idempotence, and it's like two people from Temporal, but one acts like they're not at Temporal. And I think these kind of things have showcased how difficult these terms are. Determinism, idempotence, these things are major factors for this exactly one semantic kind of replayable world that we want, and yet most developers don't know how to actually enact with those concepts. Oh, thank you, Paul. Go for it, Brian.
So the approach to non-determinism here, like the way I would put it, is they're essentially taking non-deterministic things like timestamps and freezing them in the log. Yep. And that is what gives you the replayability. Is that like I think that Micklejohn's, I was just glancing through Micklejohn's thing, but he says they determinize them or make them determinized. And
determinization of them. Yeah, that's
right. Yeah. But in this paper, they call them impulses, and this isn't like deep to the understanding, but like, but do we have any ideas about why they call them impulses?
Yeah, that's a good question. Actually, I don't know if they specifically call out why the name, and actually maybe the other paper. And I'll have to get the link. I'll put it in the thing after, which is like the paper that actually Micklejohn mentioned. Because actually, I was a little upset in this version, again, the published version, that they talk about essentially self-RPCing, but actually in this version that I linked, that's again the published version, they don't use the term self-RPC. It's in the other version of the paper, which is like an earlier version, just an earlier version before publication. And but nonetheless, to this whole point, this idea of like, I don't know why they named it impulses. I mean, my guess is, so the term, and again, they're not microservice oriented in this paper, but the term like impulse, I mean, in the workflow world, they use things around things that can be non-deterministic, essentially these things called like activities that comes from the durable history, durable functions, durable tasks, everything like this. My guess with impulses is that impulses are, at least when you think of the word impulse, right? Like something that, you just kind of do. And I think it's again, it's like this thing just happens and you want to like control it. Maybe like that's the,
I mean, I'd be delighted.
Determinism is like an impulse.
I'd be delighted if it was something like when you go to the grocery store and you've got your shopping list, but then you have an impulse buy, something like that.
Exactly. Right. And we have to protect you against this, right? Like, what if the impulse buy fails, right? Yeah, no, 100%, right.
Paul, want to
And
go
oh,
into physics for 30 seconds? I can help you with that.
Oh.
So it turns out
Go for
that
it.
physicists for a long time have worried about this issue of like instantaneous things. And one of them is called the Dirac delta function, and the other one's called the Heaviside step function. And the interesting question when it comes to distributed systems is, what are our assumptions about the nature of time when we're making statements like impulse or determinism? What was the word you used? Determinize. The problem is, Edward Lee describes this brilliantly in his book, as well as in the conversation he had with me on the It's About Time Club a few weeks ago. Edward Lee basically says there's a point. The problem is real lines are not real. This is the Chaitin thing. If you try to measure something, an interval, exactly between one point and another point, you can certainly determine an event, which is one of them, but you can never determine the second event, and the reason is because your measurement of the real line is necessarily restricted by how much information that you could put into that floating point number, or that that integer, if you wanted to use integers. And so when you discretize a measurement, when you taking something that happens in the electronics that's touching the real world, and it gives you a crude version of that with an integer or whatever else, then the problem is we're assuming that there is always this diffeomorphic relationship between what's going on in reality compared to what's happening on what our computers can see. Now, you're looking at, I'll be really honest with you, you're looking at a real life Bell system measurement here. It's like we just haven't interpreted it that way in computer science. But anyway, that's why the word impulse and is such an interesting word, because it takes a lot of interaction to excavate all of the digital, all of the decimal point, the numbers past the decimal point. You have to have continuous interactions to do that. And we don't do that in our systems. We like to take snapshots of things and say, we can freeze the timestamps.
Yeah, right. Or everybody's running the same time. No, yeah, I mean, yeah, for sure. Yeah, that's great. That's great context. Yeah, I mean, I think, I mean, this Halian non-determinism, I mean, like they talk about it, like with impulses that, I mean, this is a really not like novel feature of the paper, but this idea of self-RPC, or essentially like what they took all these ideas from database logging, essentially, which is if you can capture the non-deterministic choices, random, time of day, etc., and you replay it in the log, you self-RPC yourself before you make the call externally, then you can always go back again from essentially that seed of that information from the state that you have locally again, and always use that same information, right? And that's really the key for people, the rest of the people on this call, I would say, like that's trying to get out of here. And again, the panacea, like, again, the one thing that Lambda, got very popular, it's been so great, but the one thing it doesn't care about at all, I'm not saying that internally at Amazon, AWS, they don't care about this. They have systems that are trying to do these things, but Lambda on its own accord does not care about these kinds of semantics. It's kind of, it's really left on you, even though it gets rid of some of the other things that we've had to deal with, probably you could say, from people who were working back and having to deal with everything in terms of state and mechanics for running a server before, and running functionality and infrastructure. But it doesn't really care about these really kind of semantic concepts. And the truth is, developers have a hard time. Chris gave me a really good story of somebody at Microsoft who, was working with a database records of a user, and they're like, oh, when you get a record from the database, you get a user from the database, that's deterministic. And he's like, how is that possible? It comes with a timestamp. And people don't understand, like when you get a record from the database, just because there was no edit or update to that user, you're looking at a view in time of that user in the database. And yes, maybe they didn't change their credit card yet or their whatever. And that might not change, but it could eventually change, right? And so, again, that even well-to-do, really experienced programmers can't understand these concepts, is why we need systems that can almost kind of try to convey those pieces on behalf of the user. Now, I think that's where there's still a long line of research, because we're still, again, systems like temporal and the other things are still telling people, we hope you, like there's a link, and I have it in my talk thing, but it's like essentially on the temporal docs, they basically say, if you use an activity, please try your best to make it deterministic. Try your best is asking the developer a lot. Anyway, before we maybe talk about, I don't know if we want to talk about evaluation, some other things, anything else kind of in those kind of thinking or those kind of thoughts, or from people's backgrounds where these things might come into play. I think there's a lot of HCI-ness that's not in this paper, but kind of in and around it as well. Open it up to anybody. Or people are just like dumbfounded by this idea of virtual resiliency. And we have the commandments of it. Okay.
So I'd like to mention something briefly. I'm on the organizing committee for the Smart Next Summit in 3 weeks' time in San Jose. And one of the things that we're talking to various people about is, simplistic concepts like the CAP theorem are appallingly badly defined. And for example, the notion of consistency is the most inconsistent definition in all of computer science. And it goes with all the other C's as well, confluence and communication and coherence, and all of the C's seems to be terribly conflated. So we were talking about...
And I always preferred harvest versus yield. So.
Say that again.
I said I compared to the CAP there in particular, I always preferred harvest versus yield from Eric Brewer. Anyway, harvest versus yield has been
Could you shut the fuck up? Long story here. I heard about the CAP theorem first of all from Eric when I was going to acquire his company 22 years ago at Veritas. We were going to acquire the company he had then. We decided not to, but he told me then about this idea of 2 out of 3 of these things. And I looked him in the eye and I said, Eric, that's not going to work. And his reply was really interesting. He said, yeah, I know it won't work. But the problem is the entire distributed systems community is so confused about this. They need a handle to kind of simplify their reasoning. And this is the best we can do so far. Now, he never actually says that in his paper when he finally published it, but it was funny. It's funny that he said that. So there is something else going on though. There is this movement from the CAP theorem to the Cal theorem, which is what Edward Lee is doing, and it's very interesting. It's another take on a very sophisticated form of logical timestamps, but they have constraints in them in ways that you can put constraints on availability or constraints on latency, which are related to business logic that's needed. It's a very brave attempt. It's quite good. So we're talking about putting here's the joke. We're going to put the CRAP in the SmartNIC, and obviously CAP R stands for reliability, because no one really thinks about that. And of course, I could probably use a different acronym here with virtual resiliency or something, and find a way of saying that without being scatological.
Yeah, I know that makes sense. When I was at Comcast, we had looked at a lot of this stuff too. It does make sense to essentially with these SmartNICs to put more into that. I think that's the right approach. So it was really interesting. We used to do a lot of thinking around things like P4 and stuff like this with working with SmartNICs and smart switches with the Tofinos. Though I guess the interesting news that I haven't really kept up with a lot of personal stuff going on, but that Intel has dropped the barefoot Tofino switch kind of migration that they were doing, which has made people who work in P4, for example, which is a data plane processing language, very hey, what are our goals again? Which has been a really interesting email set of threads that I've been getting that I haven't really paid attention too much to, but I thought that was pretty interesting.
Well, if you've got something to say, we might be able to put some conversations about this in the Smart Next Summit. It's going to be a 3-day conference in San Jose. Unfortunately, it's not Zoomed. but we do have some, pretty good people coming to talk to us about that. And it's more of an industry conference than it is an academic conference.
Right.
These issues come up all the time. And it's really about this paper is, can we put the virtual resiliency in the SmartNIC? That's a very good concept. And I'd like to go as far as saying that the current idea of SmartNICs is that you can take something that you do in a host processor very expensively with the host processor tax, both time and money and energy and everything else. And if you put it in the SmartNIC, you can do it faster, cheaper, and with a lot less, non-determinism. I think that's a way that.
Yeah, and obviously the ability to install SmartNICs in very different, physical locations and situations around edge and all these things as well that are obviously taking shape.
So the idea is, can we take virtual resiliency and put it in the SmartNIC? And so the question, which I'd present to you, ladies and gentlemen, is, are there things that the SmartNIC can do that you cannot do in the main processor? And there was a great, on the IP blog recently, there was a great discussion with Gao about you cannot, let me put it, I'll try not to slow you down. Basically is saying that you cannot get the ordering of events when you're using multiple cores. It's impossible. And I have never heard that expressed as an impossibility result before, but we're acutely aware of it being impossible, or at least in practice, and in the way that we're doing things. And so the idea is there are other things in this that you can do in the SmartNIC, such as this virtual resiliency, that you cannot do in the host processor. Anyway, that's the interesting question.
Yeah, that makes sense. I do wonder how much, though, at least when I looked at some of the stuff again in the networking space and this for the next, it was how far you can get with program. Like, what is the programmability of these things for more common developers, right? That was always an issue with, and things have gotten better. Like P4 again, being for switches and stuff was kind of was an attempt at this idea, or things like it's going more on the switch level, but things like data plane processing kit from Intel. And these other kind of systems to try to make I mean, there's like Go library on top of that, stuff like that, to make this the thing that we always found with all this work in programmable networks was programmable networks still needed network programmers, which and I don't know if the Ambrosia paper in particular highlights that. I think it's interesting because Brian, you mentioned obviously they have the the evaluation and they demo like time travel debugging, which we always think from a UI perspective, right? Like how many times do you see somebody do the time travel debugger in UI? And this is but this is like in a system, right? A distributed system, and even though actually everything is really a distributed system at hand, in a system like this, you don't normally see that. This ability to have have that kind of debugger, have that kind of thing. And I think, what this paper at least gets me thinking about or alludes to is making it where operating with complex systems could essentially be done by anybody who can program some versus somebody who really has to know a certain domain. And I think knowing if something's replayable or deterministic or exactly once or at most once if you do it differently, obviously you do want engineers and software people to be able to know those at some level to know those things. But for people just who want to get some, why Lambda got popular is it made it where any, people can just kind of do this stuff. And now they can do it through their Netlify or their Vercel, whatever. They might not. The problem is, when things go wrong, they don't know how to handle it, and I think this paper is trying to solve that part of it, right?
Yeah,
I will say that. Yeah, go for
it. And it seems like it's not just my intuition is that it seems like it's not just the time traveling part, but it's the fact that it kind of unifies what's happening across a lot of different machines and gives you like a unified view.
Yeah, I want to quote this thing from the paper, and then I want to get to Dan had a question that I thought was really good. But from the paper, they talk about this, and again, a little modified toward their kind of C# lens. But Application developers no longer write logic to recover from partial executions. Then this is all handled by the immortal, the coordinator. For the same reason, they no longer have to write code to retrieve and store state, since all state is made implicitly durable through logging. And so this is a little bit in this paper. There's other papers that do this better, but I think it's this concept again, like where application developers have to reason less, but yet still get the power that comes with things. And then what, replayability is really great. If you get replayability, you get the ability to do incremental compute, which is the whole key as we do more and more large sets of processing, right? One of the big keys. So I think there is like this element of giving a developer less to have to worry about, but more power at the disposal. That's at least what I get a lot out of virtual resiliency as well. And I think to the SmartNIC stuff that you're mentioning, Paul, I think that's the next, kind of thing to figure out. Can we make it where programmers who are not as familiar with certain concepts of, layers 2 through 4 in the network stack can write programs, right? And gain the thing. Dan, you had a question. Go. I heard you there. Sorry.
Was my mic on?
Yeah, it was. Oh, sorry. No worries.
That's funny. Sorry. I didn't even know it was. So, well, I unfortunately, I'm not a computer scientist. I've had to write some code throughout my career, but I do have a computer science or a cognitive science PhD, and our field had suffered a lot from this. The physics envy, and I know once in a while, taxonomy papers come out. People put together these compendiums, but they're really taxonomy papers, because if not, the whole community is just talking across each other, and everybody knows what. Yeah, I know what attention means, right? And then we start to find that other fields extrapolate it, and then it gets worse. Right. So now everybody talks about attention as in LLMs and things like that, and transformers. Right. So I just brought that up because I wonder if it would be useful. And I personally do have an interest in ontology, and I'm looking into, for other reasons. Kind of Web3.
Yeah. No.
Web is right.
No, I agree with you. I think there is a lack of this kind of, into Paul's point earlier with, what we knew as a CAP theorem and what that meant, but actually didn't really cover everything so we mentioned Harvard deal. All these terms, right? We know, and then there's like all this cross boundary between the systems work and distributed systems, and of course in networking, to a lot of Paul's points as well there, essentially the ontology of things is kind of baked into the references within papers, and you have to kind of follow these trails. And that's actually, I agree, it's actually very difficult and too academic, right? There should be better ways to cross these lines. Maybe it's something we can kind of think about here. Even for me, so I came from a web, it's always weird to say this, a Web 2 world, I guess, and now I work in Fission, which is, in a Web 3 world, I guess. And though not always, chain related, which I think is also a thing that people misconstrue a lot too, within Web 3, I guess. But I'm, like this Ambrosia paper, obviously not in a Web3 space, but has been the kind of one of the big foray papers for our work, again, on IP, on this, interplanetary virtual machine work, which is, again, geared toward Web3 and working with IPFS. So there's even this kind of cross channel, right, between like, when I came to this space, like, I bring up all these like workflow engine stuff, and I'm at a talk in Brussels for Protocol Labs, and people are like, what are you talking about? Like, we have no clue what this is at all. And I think, or let alone what people and other things might know about content addressable data, right? So it goes the other way too, right? And so I think, even though these content addressing has existed for forever, Akamai was the first to do content address work, in terms of networks and switches, right? So to the whole point on this, I think I agree with you. There needs to be a better view on the ontology of how we can talk about these things, and it's there. It's just very academic, and actually the conference that's kind of best for these things is a great ACM conference about survey. It's like a conference just on survey papers, but it's only, I think, every couple of years, and obviously covers a lot of things, and there hasn't really been, I think, a definitive kind of systems literature kind of record survey of all these things. They might focus on blockchains, they might focus on this, but not all these terms. And there's a lot. So you know, I can understand why it's so confusing. Maybe that's what we'll do when we come out of it. Actually, I think our next paper for the next time we meet, I forget the ordering, which one I have which, but one of them in the next two is actually like a survey paper on schedulers. And so it's a paper from the, I think, late 80s. But we're going to be going through all the different scheduling algorithms, which, you know, it's kind of toward this idea. At least here are some papers that like convey what is out there and why, what are the trade-offs and what are the right terms, right?
That is the next one.
Yeah, good, cool. I did it right that way, yeah. But you know, even that's with scheduling algorithms, right? And so you can have 40 pages or 20 pages or whatever just on that, you know, let alone like, how can we create a whole system space? I mean, stuff that Paul's doing with podcasts on this, you know, we've also lost a lot. Like, I think, you know, there used to be I think like podcasts are really good and these kind of things to put things in perspectives. Chris Micklejohn used to run one back in the day called Think Distributed, which was really great. You know, he actually has a little bit of a podcast he started, but I think they've only gotten to 3 or 4. Obviously, there's so many things, but you know, yeah, there's not a lot of stuff that kind of tackles this, and you know, again, non-academic settings. I think would be really great. I know we started a little late, but as we come to the hour, anyone else with any other thoughts on this paper or virtual resiliency, and how it might, you know, mean something for them? I'll leave it up for anybody at the end here. Those thoughts. Cool. I think that's where we're at. But go for it, Brian. Good. Thank you, Brian.
I was giving other folks an opportunity, but so, I mean, like at the end of the day, this whole system relies on like a single centralized database, right?
That is correct.
And so, I mean, like when I was first like doing the first pass through the paper, they were talking about that I hadn't gotten to that part. And I was thinking actually, about
even though that's the way it's deployed, it actually, you know, technically is from peer to peer though, within a centralized system of peer to peer, a controlled system of peer to peer. Anyway, I just want to say that it is technically a, you know, node to node.
Well, but the durable log has to be in a database that's shared between each of the peers.
Of course.
Right?
Oh yeah. The storage is definitely centralized. Yes, 100%. Right. Correct.
Yeah. Right. So like before I had gotten to that part, I was reading about the logging and the sort of logging mechanism. And they make this claim early in the paper about how you could offload to a Raspberry Pi. And I was immediately thinking like, well, yeah, but a Raspberry Pi is not going to have much storage. Okay, cool. We're like have, you know, like a centralized store or whatever. But I mean, how realistic do we feel like this offloading to a Raspberry Pi thing is? You know, like, is this really more about like a bunch of machines running in the cloud working together, or is this something that my Raspberry Pi at home could participate in?
Well, I'd like to. So first of all, the concept here is that you're pushing something off into another failure domain. In other words, you're getting out of all of the messed up assumptions we often have about how failures are independent, which because they're not. So by pushing the concept of pushing it out to some failure domain, which has its own power supply, which has its own battery, which has its own persistent memory, I think is the key idea here. No, it doesn't have to be a Raspberry Pi, it can be anything, but it kind of forces your reasoning to be, well, look, really be careful about how independent those failures are in that other domain. And I think that's a decent idea. We're also doing something similar with, we've been approached to try to say, how can we synchronize clocks in a swarm of nano spacecraft that are being launched for to Proxima Centauri, and the idea is they wanted to take a 20-year trip to Proxima Centauri and return pictures, and they've discovered that the killer application there is synchronized clocks. And we're using that as an example. It's not science fiction, by the way. There's serious engineering going on here. They expect to push these things towards, if they're small enough, to push them to like 20% of the speed of light, which gets them there faster than you would expect. But the engineering is really interesting because you can't have a single point controller there, because it gets hit, all of them are gone. And so we're going to be giving a talk, I think, in a couple of weeks on this this idea of synchronized clocks in satellites. And I think the idea of like, how do we get our thinking out of the box that we're in right now and putting it onto a Raspberry Pi, I think is that style of like getting you out of the box of thinking.
Yeah, that's a great answer. I go for it, Brian.
So we only have a couple of minutes left, so maybe we won't have time to get into this. But when they're in section 3.1, they kind of go through the overview of like the immortals and how each immortal has an immortal coordinator, and then the actual application and the ambrosia binding. And they make the point that like, oh, the immortals can fail, or an immortal can fail, but the others will pick up the slack. And one failure mode that they didn't mention that I was kind of curious about is, what if either the immortal coordinator or the application fail, like just one of the processes fail, but the entire machine doesn't go down? Are there problems that could come out of that? I'm not like pointing at one or saying like I think this is an issue, but like,
yeah. So you're saying like one issue is just like on a single core versus on the rest of the cores, for example, running some of this stuff, something like that is what you're kind of asking about, like a process, but not the system. Yeah. I mean, my guess, and maybe they don't cover it, my guess though is in the system is that like we have health checks and things across systems, we typically, when we work in across concurrency, we have ways to kind of check, okay, this thread has spun out and is like just doing work for nothing. We know how to like kill those things within the context of that node itself. So my guess would be there's things that we do to essentially cover those kinds of things in systems all the time, at the process level. Watching processes, these things are pretty common. I mean, obviously, Ambrosia is also references a lot of Orleans and Erlang. And Erlang, again, even though there's distributed Erlang really was a concurrent system, and the ability to kind of, deal with process failure was super part of the Erlang actor model, for example, for sure. And so to me, because that was the influence anyway, I would think they would probably use something very similar within their framework for that.
Makes sense.
To your previous question on pies, though, I wanted to get at before we end here is that, there is obviously stuff with like how much storage and things, but people are doing like fleets of this stuff too, right? Like it's not about one Raspberry Pi. That's like the very at-home case. Eleanor had a great page at bottom 4. They state that they expect both to fail, both recover together. That's also like an answer from the paper. It's awesome.
Yeah.
But I would say like people are doing stuff with like FPGAs and all this stuff now, where they're running huge tiers of these things, at scale. They're all separate instances, right? Or like people who do many pies, right? And so, I think Paul's point, it doesn't have to be centralized. It's just that you still need to, if you're going to offload a lot of that power and a lot of that storage, you still need essentially a lot of instances you have to like make it up by still having lots of hardware somewhere, right? So, but of course, the massive issues of failure, it would be obviously, I think what you capture though is that the evaluation doesn't capture a Raspberry Pi, like a set of Raspberry Pis and a bunch of stuff failing all over the place, right?
Yeah.
Which is, an interesting evaluation that we would all want to see, right? But yeah. Cool. All right. Well, yeah, thank you for that, Eleanor, for the bottom of the page. Again, we've been looking at this paper a lot of fission, so a bunch of people are down to talk more about this and some of the other related work. And I'll put this video up soon, and we have a meeting, I think, pretty soon. I think we only have like a week or a couple of weeks, I think, before the next one. So Take care, everybody.
Bye.